A gear or cogwheel is a rotating machine part having cut teeth, or cogs, which mesh with another toothed part to transmit torque. Geared devices can change the speed, torque, and direction of a power source. Gears almost always produce a change in torque, creating a mechanical advantage through the gear ratio, and thus may be considered a simple machine. The teeth on the two meshing gears all have the same shape. Two or more meshing gears working in a sequence are called a gear train or a transmission. A gear can mesh with a linear toothed part, called a rack, thereby producing translation instead of rotation. The gears in a transmission are analogous to the wheels in a crossed belt pulley system. An advantage of gears is that the teeth of a gear prevent slippage. When two gears mesh, if one gear is bigger than the other, a mechanical advantage is produced, with the rotational speeds and the torques of the two gears differing in proportion to the diameters. In transmissions with multiple gear ratios, such as bicycles, motorcycles, and cars, the term gear, as in first gear, refers to a gear ratio rather than an actual physical gear. The term describes similar devices, even when the gear ratio is continuous rather than discrete, or when the device does not actually contain gears, as in a continuously variable transmission. History. Early examples of gears date from the 4th century BCE in China, which have been preserved at the Luoyang Museum of Henan Province, China. The earliest gears in Europe were circa CE 50 by Hero of Alexandria, but they can be traced back to the Greek mechanics of the Alexandrian school in the 3rd century BCE and were greatly developed by the Greek polymath Archimedes. Examples of further development include margin-used gears as part of a south-pointing chariot. The Antikythera mechanism is an example of a very early and intricate geared device, designed to calculate astronomical positions. Its time of construction is now estimated between 150 and 100 BCE. The water-powered grain mill, the water-powered sawmill, fulling mill, and other applications of watermill often used gears. The first mechanical clocks were built in CE 725. The 1386 Salisbury Cathedral clock may be the world's oldest working mechanical clock. Comparison with drive mechanisms. The definite velocity ratio that teeth give gears provides an advantage over other drives in precision machines such as watches that depend upon an exact velocity ratio. In cases where driver and follower are proximal, gears also have an advantage over other drives in the reduced number of parts required. The downside is that gears are more expensive to manufacture and their lubrication requirements may impose a higher operating cost per hour. Backlash. Backlash is the error in motion that occurs when gears change direction. It exists because there is always some gap between the trailing face of the driving tooth and the leading face of the tooth behind it on the driven gear, and the gap must be closed before force can be transferred in the new direction. The term backlash can also be used to refer to the size of the gap, not just the phenomenon it causes. Thus, one could speak of a pair of gears as having, for example, 0.1 mm of backlash. A pair of gears could be designed to have zero backlash, but this would presuppose perfection in manufacturing, uniform thermal expansion characteristics throughout the system, and no lubricant. Therefore, gear pairs are designed to have some backlash. It is usually provided by reducing the tooth thickness of each gear by half the desired gap distance. In the case of a large gear and a small pinion, however, the backlash is usually taken entirely off the gear and the pinion is given full-size teeth. Backlash can also be provided by moving the gears further apart. The backlash of a gear train equals the sum of the backlash backlash of each pair of gears. So in long trains, backlash can become a problem. For situations that require precision, such as instrumentation and control, backlash can be minimized through one of several techniques. For instance, the gear can be split along a plane perpendicular to the axis, one half fixed to the shaft in the usual manner, the other half placed alongside it, free to rotate about the shaft, but with springs between the two halves providing relative torque between them, so that one achieves, in effect, a single gear with expanding teeth. Another method involves tapering the teeth in the axial direction and letting the gear slide in the axial direction to take up slack. Shifting of gears. In some machines it is necessary to alter the gear ratio to suit the task, a process known as gear shifting or changing gear. There are several ways of shifting gears, for example, manual transmission, automatic transmission, derailleur gears, which are actually sprockets in combination with a roller chain, hub gears. There are several outcomes of gear shifting in motor vehicles. In the case of vehicle noise emissions, there are higher sound levels emitted when the vehicle is engaged in lower gears. The design life of the lower ratio gears is shorter, so cheaper gears may be used, which tend to generate more noise due to smaller overlap ratio and a lower mesh stiffness, etc., than the helical gears used for the high ratios. This fact has been used to analyze vehicle-generated sounds since the late 1960s, and has been incorporated into the simulation of urban roadway noise and corresponding design of urban noise barriers along roadways. Tooth profile. A profile is one side of a tooth in a cross-section between the outside circle and the root circle. Usually a profile is the curve of intersection of a tooth surface and a planar surface normal to the pitch surface, such as the transverse normal, or axial plane. The fillet curve is the concave portion of the tooth profile where it joins the bottom of the tooth space. As mentioned near the beginning of the article, the attainment of a non-fluctuating velocity ratio is dependent on the profile of the teeth. Friction and wear between two gears is also dependent on the tooth profile. There are a great many tooth profiles that provides a constant velocity ratio. In many cases, given an arbitrary tooth shape, it is possible to develop a tooth profile for the mating gear that provides a constant velocity ratio. However, two constant velocity tooth profiles are the most commonly used in modern times, the cycloid and the involute. The cycloid was more common until the late 1800s. Since then, the involute has largely superseded it, particularly in drivetrain applications. The cycloid is in some ways the more interesting and flexible shape. However, the involute has two advantages. It is easier to manufacture, and it permits the center-to-center spacing of the gears to vary over some range without ruining the constancy of the velocity ratio. Cycloidal gears only work properly if the center spacing is exactly right. Cycloidal gears are still used in mechanical clocks. An undercut is a condition in generated gear teeth when any part of the fillet curve lies inside of a line drawn tangent to the working profile at its point of juncture with the fillet. Undercut may be deliberately introduced to facilitate finishing operations. With undercut, the fillet curve intersects the working profile. Without undercut, the fillet curve and the working profile have a common tangent. Gear materials. Numerous non-ferrous alloys, cast irons, powder metallurgy and plastics are used in the manufacture of gears. However, steels are most commonly used because of the high strength-to-weight ratio and low cost. Plastic is commonly used where cost to weight is a concern. A properly designed plastic gear can replace steel in many cases because it has many desirable properties, including dirt tolerance, low-speed meshing, the ability to skip quite well, and the ability to be made with materials that don't need additional lubrication. Manufacturers have used plastic gears to reduce costs in consumer items including copy machines, optical storage devices, cheap dynamos, consumer audio equipment, servo motors, and printers. Another advantage of the use of plastics, formerly, was the reduction of repair costs for certain expensive machines. In cases of severe jamming, the plastic gear teeth would be torn free of the substrate, allowing the drive mechanism to then spin freely. This use of sacrificial gear teeth avoided destroying the much more expensive motor and related parts. This method has been superseded, in more recent designs, by the use of clutches and torque current limited motors, standard pitches and the module system. Although gears can be made with any pitch, for convenience and interchangeability standard pitches are frequently used. Pitch is a property associated with linear dimensions and so differs whether the standard values are in the imperial or metric systems. Using inch measurements, standard diametral pitch values with units of per inch are chosen. The diametral pitch is the number of teeth on a gear of 1 inch pitch diameter. Common standard values for spur gears are 3, 4, 5, 6, 8, 10, 12, 16, 20, 24, 32, 48, 64, 72, 80, 96, 100, 120, and 200. Certain standard pitches such as 1/10 and 1/20 in inch measurements which mesh with linear are actually circular pitch values with units of inches. When gear dimensions are in the metric system, the pitch specification is generally in terms of module or modulus, which is effectively a length measurement across the pitch diameter. The term module is understood to mean the pitch diameter in millimeters divided by the number of teeth. When the module is based upon inch measurements, it is known as the English module to avoid confusion with the metric module. Module is a direct dimension, unlike diametral pitch, which is an inverse dimension. Thus, if the pitch diameter of a gear is 40 mm and the number of teeth 20, the module is 2, which means that there are 2 mm of pitch diameter for each tooth. The preferred standard module values are 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.8, 1.0, 1.25, 1.5, 2.0, 2.5, 3, 4, 5, 6, 8, 10, 12, 16, 20, 25, 32, 40 and 50. Manufacture. As of 2014, an estimated 80% of all gearing produced worldwide is produced by net shape molding. Molded gearing is usually either powder metallurgy or plastic. Many gears are done when they leave the mold, but powdered metal gears require sintering and sand castings, or investment castings require gear cutting or other machining to finish them. The most common form of gear cutting is hobbing, but gear shaping, milling, and broaching also exist. 3D printing as a production method is expanding rapidly. For metal gears in the transmissions of cars and trucks, the teeth are heat-treated to make them hard and more wear-resistant while leaving the core soft and tough. For large gears that are prone to warp, a quench press is used. Inspection. Overall gear geometry can be inspected and verified using various methods such as industrial CT scanning, coordinate measuring machines, white light scanner or laser scanning. Particularly useful for plastic gears, industrial CT scanning can inspect internal geometry and imperfections such as porosity. Important dimensional variations of gears result from variations in the combinations of the dimensions of the tools used to manufacture them. An important parameter for meshing qualities such as backlash and noise generation is the variation of the actual contact point as the gear rotates, or the instantaneous pitch radius. Precision gears were frequently inspected by a method that produced a paper gear tape record showing variations with a resolution of 0.001 inches as the gear was rotated. The American Gear Manufacturers Association was organized in 1916 to formulate quality standards for gear inspection to reduce noise from automotive timing gears. In 1993, AGMA assumed leadership of the ISO committee governing international standards for gearing. The ANSI AGMA 2000-A88 Gear Classification and Inspection Handbook specifies quality numbers from Q3 to Q15 to represent the accuracy of tooth geometry. The higher the number, the better the tolerance. Some dimensions can be measured to millionths of an inch in controlled environment rooms. Gear model in modern physics. Modern physics adopted the gear model in different ways. In the 19th century, James Clerk Maxwell developed a model of electromagnetism in which magnetic field lines were rotating tubes of incompressible fluid. Maxwell used a gear wheel and called it an idle wheel to explain the electric current as a rotation of particles in opposite directions to that of the rotating field lines. More recently, quantum physics uses quantum gears in the model. A group of gears can serve as a model for several different systems, such as an artificially constructed nanomechanical device or a group of ring molecules. The three-wave hypothesis compares the wave-particle duality to a bevel gear. Gear mechanism in natural world. The gear mechanism was previously considered exclusively artificial, but in 2013, scientists from the University of Cambridge announced the discovery that the juvenile form of a common insecticus, found in many European gardens, has a gear-like mechanism in its hind legs. Each leg has joints that form two 180-degree helix-shaped strips with 12 fully interlocking spur-type gear teeth. The joint rotates like mechanical gears and synchronizes its legs when it jumps.